Good afternoon. So this is one lesson that I will not ask you to read it in the book, so you can just read my notes only. I mean, my notes are enough even if you want to read the exam. So this one, I want to start the Banach fixed theorem. We need some definitions and one big theorem that, of course, I want to give the proof for you, but I mean, it's a very interesting and nice proof, okay? So the first thing we need to know is very elementary, but of course, you have the notion of metric space, so it couldn't be that elementary, but the idea is very simple, and that is the notion of a fixed point. Yes, you have a metric space x and d, and then you have a map that takes elements from x to x. And a point in x is called a fixed point if phi cannot change it. It maps it into itself. So if we want to talk about definition 8.1, so you have a metric space okay, and then you have a phi, a function whose domain is x and its codomain is also x. So I'm not saying that the range is x, but the codomain is x, the domain is x. This function you have, and then you say p in x is called a fixed point. Of phi if, very simple, so phi acting on p gives p. It doesn't change p. That's called a constant point of a function. Yes? For example, in here I have asked you determine all fixed points of the following function. It's just a high school problem. Yes? So I have given you a phi x 8.2. Phi x is defined from R to R. Phi x is this very simple polynomial 2x squared plus 3x. And I am asking you find all possible fixed points for this. So what does it mean? According to the definition, P is a fixed point if phi cannot change it. Otherwise, in other words, phi acting on P gives you P and you are looking for this fixed point P. So you just solve an equation, yes? So phi of P means 2P squared plus 3P is equal to P, and this means that I bring P to the other side, so 2P squared plus 2P is 0, and I factor 2P, so it becomes P plus 1 equal to 0, and I get two constant values, yes? So P is equal to 0, or P is equal to 0. Yes? Simple. Do you want this as an exam question? Yes, yes. So this is a fixed point. But now the point is that there is another nice thing coming after that. Why we really care about fixed points? Sorry. For example, you know that one of the problems we want to solve in mathematics is solving equations. Yes, what is an equation? So I'm just talking about this remark. So what is an equation? An equation is an equality in which you have some unknown. Let us start with one unknown here, but on the left-hand side you have a relation on x, so I will call it f of x, and on the right-hand side I have an equation, an expression in x. So an equation in one unknown is an equality of this form. Yes, do you agree? Some part. So if I ask you to solve this equation, you have some methods, probably you will use those methods to solve them, but I want you to understand this problem can be rephrased in the form of the constant point, a fixed point. How? For example, I have written it in the notes. For example, if you want to solve this, this is equivalent to saying that f of x minus g of x is equal to 0, and this is equivalent to saying that f of x minus g of x plus x is equal to x. Yes? So I hope that you agree that what I have written here is mathematically equivalent to what I have written here now. But what is the problem? The problem is if I call this phi of x, then what happens? This becomes equivalent to phi x equals to x. So it means that I can reformulate my equation question to finding a fixed point for a different phi. So if I can define an appropriate phi, solving my equation is equivalent to finding the fixed point of that particular phi. And I will see there are some examples we will solve today. That it is, of course, I mean, the idea is very clear. So is that clear what I'm saying? I'm saying that equations like this can be reformulated to finding fixed point of another function appropriately defined. Okay, so that's the content of this remark here. Okay, is there something I am missing? Okay, the most important result for us is the contraction mapping theorem. I don't know, I shouldn't have written this here because you haven't heard about this. This is in the next slide. I will probably fix it a little bit later. Okay, so now this is another definition, which is also very important for us. Definition, contraction map. Again, we are working in a metric space. So x and d, a metric space. Phi is a function from x to x. We say that phi is a contraction on x if there exists a real number lambda is strictly less than 1, greater than or equal to 0, such that the distance between phi x and phi y is less than or equal to lambda times the distance between x and y for all x and y in x. So if I want to write it here on the board, so again, what do I have? I have a metric space. Yes, I have a phi from x to x. If I want to call this phi a contraction map, it should have some property. If there exists a lambda where in the open, so in the interval from 0 to 1, 1 open, 0 could be included. If there exists this such that for all x and y in x, the distance between phi x and phi y. What is the distance here? Does this distance make sense? Why? Because this range is also x. So phi x and phi y takes off x and y are in x. Phi x and phi y are again in x. So it's important. Okay? So these are 2 points in the same metric space, so I can apply d for finding the distance between them. Yes? So I am saying that if you can find this number with this property, so that for every x and y in the metric space, the distance between the outputs is less than or equal to lambda times the distance between the inputs, then I call phi a contraction on x. So phi, then phi is called a contraction on x. Yes. By the way, the lecture notes are also on the website. I was working on them just before coming, so it is there. If you want, you can have access to it. Okay, any questions? What is the meaning of this geometrically? It means that, for example, if this is x and this is also x, phi goes from x to x. It means that if I have this distance, for example, if this is x and this is y, this is this distance. This distance for every pair will be reduced, okay? Because it is being multiplied by a factor which is strictly less than 1. So this means that, for example, phi x goes here and phi y goes here, so that the distance, the new distance, is smaller than the old distance. By what factor? By factor of lambda. And not by factor, might be smaller even than the factor of lambda. But contraction is a good name because it contracts. So what is the strongest contraction? if you are very, very strong, you can press everything into one point. What is it called then? What that contraction is called? Yeah, there is a name for it. Who can crush you, dictator? Do you remember I told you which function is the dictator of mathematics? Which one is the most liberal? So these are the mnemonics that you can remember. These are the names. So the liberal one is the identity. Whatever you say, I say the same thing. Yes, f of x is equal to x. But the adamant, the dictator, is that I don't care what you say, I say my word. That is called the constant function. Yes? So it means that, do you agree the constant function is the strongest one? Because if it's a constant function, it takes all these pairs to one single point. So actually they crush them. Okay, so there is no distance anymore left. Okay, and that corresponds to which value for lambda? 0. Do you feel that? Because if lambda is 0, the distance between them is less than or equal to 0. But the distance cannot be less than 0. Automatically, it means that it should be equal to 0. So it means phi x and phi y should be the same for every pair. That means that the function is constant. Understandable? So the constant function is the strongest contraction function. Okay, and it corresponds to the value for 0. So that's why 0 is included. You will see that 1 is not, if I choose 1, there is no guarantee because might be the distances remain the same. And you will see in the proof that is coming, 1 is problematic. Okay, and numbers greater than 1 will also be problematic because they will not necessarily shrink the distances. Is that clear? Okay, so now this is the meaning. Again, be careful. Existence of lambda comes first. Existence first, then quantifier. So you know that in logic, in principle, you cannot interchange an existential quantifier with a universal quantifier. So you can always interchange two existential quantifiers. You can always interchange two universal quantifiers. But it is extremely important that you cannot change this the other way around. For example, you see that which one is correct? For all x, there exists a y in real numbers so that x plus y is equal to 0. Let me interchange them. For there exists a y for every x, x plus y is equal to 0. So which one is true, which one is false? Because if one of them is true, one of them is false, it means that I am not allowed to interchange universal and existential quantifier. So now I want you to learn that because this will be important for the next chapter. And also here, you see, existence comes first. Okay? So this means that you pick lambda which works for every pair. Okay? But if I change it, it means for every pair, there exists a lambda which might depend on the pair. If you change the pair, the lambda might also change. So here, what happens, for every x, there exists a y so that x plus y is equal to, I'm working in real numbers. X and y are real numbers. Is that true or false? Every number that you give me, there is a number that you can also give me so that when I add them, it becomes 0. But the next one is wrong because it tells me that you can give me a number, y, so that when I add it to every other number, the result is 0. But we don't have that one. Do you understand that? So this is true, this is false. So this is just an introduction because in the next chapter, continuity, this becomes important. Okay. So anyway, no questions regarding this? Okay, let us go to the next one, which is the climax of today's lesson, and that's contraction map theory. Okay, I want to go through the proof, but I will of course not ask the proof in the exam, but there are some techniques in the proof that you might learn, which would be useful for exam questions. Okay, I will point them out. So what is the contraction map theorem first? Let X and D be a complete metric space and let phi be a contraction. Contraction on X, I mean. Then phi has a unique fixed point in X. So it is combining those previous notions. The notion of fixed point, that is why I defined it for you first, and the notion of contract point, and the notion of completeness we learned yesterday. What was that? Which metric space is called complete? I told you two concepts are very important: compactness and completeness. Yes?
It's if all the Cauchy sequences converge?
Yes. Because we learned that every convergent sequence is Cauchy, but there is no guarantee that every Cauchy is convergent. But there are some spaces that in which every Cauchy is also convergent, and those spaces are called complete spaces. Yes. So this contraction map theorem, this is, by the way, this is called Banach fixed theorem. So I don't know. That is also another name. So don't get confused. These two are the same names. I have forgotten to mention that. Okay, so let us write the content here. So this is theorem 8.5. So we have a complete metric space. So it means that if I have a Cauchy sequence, it is automatically convergent. If I have. So complete metric space, and then phi from x to x is a contraction. Yes. And then what I want to say is that this phi has only one fixed point in this space. So this means that the claim is this: there exists, this exclamation mark means one. So there exists only one p in what? There exists only one p in x such that phi of p is p. So that is what we want to prove. So there exists a unique, the exclamation mark means there exists a unique p in x such that phi p is equal to p. So let us write proof, okay? So the good thing about this theorem is that in the proof you see how you can find that fixed point. I remember, finding a fixed point could be elementary. Even high school students could find the fixed point of this one, okay? But if this equation is complicated, it's not that easy to find the fixed point. For example, one of the examples that I have solved for you, if I give you this equation and I ask you to find fixed point for cosine. If I give you this function and I ask you to find the fixed point of this, how do you solve it? You say that cosine p should be equal to p. But this is a transcendental equation, yes? It's not a polynomial equation that we can solve easily. So you have to solve this numerically. So it is not very clear that is there any real number whose cosine is equal to itself? So this is the same problem, but in this problem it was extremely simple to answer, but in that problem it is not. Okay, so later we will see that, of course, I have solved this problem for you in the notes, in the problem and solutions part. So you can see that the answer to this is yes. There is one unique number between 0 and 1 so that this works, using exactly this theorem. Okay, so I want you to know that this was very elementary. You didn't need Banach fixed theorem to answer that. And by the way, it was not unique. Why do you see it is not unique? Because that's not a contraction. It's not compressing. So if it is not a contraction, this might not work. Anyway, so we want to prove this is the case. So the proof is very interesting, okay? So we say that let P1 be in X. So you can choose you can choose it even randomly. You choose one P1 from your space, whatever that point is. We define the sequence Pn recursively as follows. Okay, so what is my first term? The first term is this one. But if I want to find the second term, I put the first term in phi, I get the output, this will be P2. And if I want to find P3, I put P2 in, and I get P3. So do you know recursively? This is the recursive way of defining. So it means that p n plus 1 is equal to 5 pn for all n. Is that clear? So if I want to draw a diagram here for you, so here you start with P1, randomly you choose something from X, you apply phi on it, it gives you what? It gives you the next one. Phi acting on Pn gives you the next term. It gives you P2. And then you take P2 and put it inside phi, it gives you another one, you call it P3. And then this continues, okay? What do you have now? If you look here, you have your sequence P1, P2, P3, etc. Okay, so the only thing you don't know is what P1 is, because if I give you P1, you can generate all of them because phi is given to you. But I am telling you, don't worry about P1. P1 is any number that you, is any element you like from your metric space. And now the claim is that this sequence is convergent. So my claim is that, so let me write these things, big picture claim. So let me, I don't know how to call it, big claim. Yes, the big claim is that Pn converges, okay, converges to a point P, and we show that, and phi P is P. That is your fixed point. Okay, so claim Pn converges to a point P, and phi P is equal to P, and P is the only fixed point. So this is the big claim. But when you say it's a big claim, it means it's a big project, so I have to divide it into several parts. But I want you to understand what is going on. My final goal is to show that this sequence that I defined for you, more or less randomly, because my starting point is random, it's always convergent, and it converges exactly to the fixed point of this contraction map. And that fixed point is unique. Okay? And when I say that I have a contraction, I have a scaling factor. So if you don't mind, let me put this lambda here. So lambda is my scaling factor here. So now a small claim number 1, yes? Small claim number 1 is this one. I want to prove that T dp index n plus 1, index Pn, the distance between Pn plus 1 and Pn, is less than or equal to the contraction factor to power n minus 1, the distance between P2 and P1. Okay, you might say, Babak, why we should have even this claim? Because my goal is to show that this is convergent. But because I am working in complete metric spaces, I reduce my goal to prove that this is Cauchy. Okay? If I can prove my sequence is Cauchy, because I am working in a complete metric space, automatically it becomes what? Convergent. And this is one part of my big claim. Okay? And if I want to know that a sequence is Cauchy, I have to find a way to measure the distance between the mth term and the nth term. Do you remember? In the Cauchy, do you remember? There should be a natural number so that if m and n are greater than or equal to n, then the distance between Pm and Pn is less than epsilon. So this is for making it Cauchy. This is the distance between the mth term and the nth term. But what I want to do, I want to have an estimate about the distance between two consecutive terms and try to add them up to find the distance between two farther terms. So that is why it is not a very strange idea to start with this one. And this is a good thing for exam, okay? So if you want to prove a question, is it something is Cauchy, one idea is to measure to estimate the distance between two consecutive terms and try to use the triangle inequality to find an estimate between terms which are farther apart. Okay, so that's a good technique to remember. Okay, but how can I prove this? Can you give me a suggestion? Yes, this is a claim about natural numbers, so induction. Yes, let us start with induction. So proof induction on n. So do you agree this statement? If n is equal to 1, how this statement is read? It is dp2 p1. I am replacing n with 1 everywhere. Yes, to see if it is true for 1. Yes, it is true. Do you agree it is true? Yes, because lambda to power 1 minus 1 is just 1. And dp2 p1 is less than or equal itself. That's true. And now we assume that it is true for k. Have you heard about induction? Yes? Okay. So it's less than or equal to lambda to power k, and I have d p2 and k plus k minus 1, sorry, dp1 assumed to be true. Now I want to prove this is also true for the next stage. So d pk plus 2 pk plus 1 is less than or equal to lambda to power k dp2 p1 to be proven. Yes? Okay, help me to prove this. So this one is done. This one, true or false, we assume it is true. That's the power of induction. And we want to show that the next statement is true. Can you help me? How can I show the next the next level is true? I start with this dp. What is that? K plus 2 and pk plus 1. Can you write something in terms of phi for me here? Instead of pk plus 2, do you agree that I can write phi of pk plus 1? Do you agree? Because what? You see here, phi pn is equal to the next term. So if this index is n, after phi applies on it, the index will increase by 1. Yes? So that's the same thing. So if phi acts on pk plus 1, the index will be increased. And for the same story, I can write it as phi pi k. Yes? But phi is a contraction. So this is less than or equal to the factor of contraction lambda d of pk plus 1 pk. Okay? But now, so this is phi is contraction. And this one is less than or equal. I copy and paste lambda, but d pk plus 1 and pk, according to the induction hypothesis, is less than this one. P to P. And then, of course, if you multiply these two factors, it is simply lambda to power k. And we are done. Yes? That is exactly what I wanted to prove. So this one is proof by contradiction. Okay, so another claim. So let me call this one claim. It's not that small, but let me call it claim 2. Okay. So we want to prove that Pn is Cauchy. So I was using this formula. I know more or less I can estimate the distance between two consecutive terms. But now I would say let m be greater than n. So for example, if this is your metric space, P, so for example, here is Pn and here is Pm. Okay? I want to estimate the distance between this term and that term. I want to estimate this term. But what I have in my hand is the estimate between two consecutive terms. Can you tell me what to do now? This is also good. So you see, this is the estimate between two consecutive terms. But for Cauchy, I need an estimate between two arbitrary terms. Okay? So it means let us consider these two arbitrary terms. Let us assume that m is greater than n. One of them is greater, I call the greater one n. But now I want to find an estimate between these two. The only thing I have in hand is the estimate between two consecutive terms. So how should I do that? So for example, I consider the distance between this and Pn plus 1. I have some estimate about this distance. Then I have another distance between, I don't know, so let me write it in this way. I have another estimate between Pn plus 2, yes? And then I can continue until I reach to the estimate between these two, yes? So instead of going directly for the estimate, I go through consecutive terms. So this idea you should remember for the exam as well, okay? For proving here about Cauchy. So what we can do, we can say that, okay, dp m and pn is less than or equal to, I start from the end, dpm minus 1 plus dpm minus 1. Do you agree that this is the triangle inequality? So this broken line is longer than this straight line. That's the meaning of triangle inequality. So I'm writing it from, so instead of going directly from this point to that point, I am estimating this green line segment by these broken lines, the sum of these broken lines. So this is the meaning of triangle inequality. So this one is less than this sum. Okay, so plus up to dp n plus 2 n plus 1, and then finally dp n plus 1 and pn. First of all, let me wait for you. Do you believe what I have written is true? I am telling that the distance, the green line segment, is less than the sum of all these small parts. But for technicality, as you will see, I have started from adding from bottom to the top, to the first, okay? As I'm adding like this. Yes? Is that right? Okay. But now, let me write this as a sigma. It is easier. So this sum is equal to a sigma. You see, this is dp. Let me choose an index k. And the next index is pk minus 1. Okay? But then what should I run? I run k from where to where? The smallest one. The smallest one is n plus 1. The largest one is m. Do you agree with what I have written? So I am writing it from here because this one is the smallest one. You know, n is the smaller one. You know why I did this strange way? Because in my estimate, n plus 1 is first, and the smaller one is on the right. So that is why I started this gymnastic. Might be there was a better way to do it from the beginning. But hopefully you understand it's not wrong. Yes? Is that clear? Okay, but now we can write, I can estimate this. Can you write something at least? I want to feel that you are also involved. So what should I write for this one? Less than or equal to. I have copied and pasted this sigma, and instead of this one, I can estimate it because now they are consecutive. How can I estimate consecutive ones? Lambda to the power of the lowest index minus 1, the distance between P2 and P1. So this becomes less than or equal lambda to the power of the smallest index minus 1 and then I have what? dp2 p. Let me double check everything. Yes, it seems everything is right. Do you agree with me or not? Yes? I think you are so tired that you will believe whatever I say now. Yes. So think about it. Yes? Okay. So I have written this in the form of sigma, so I double check that it's correct, hopefully. And because now every term is the distance between consecutive terms, and I have an estimate for consecutive terms, I actually use this formula over and over again. So it means that I use this formula here. But this one is a constant number which does not depend on my counter. So it's a constant. I can pull it out from my sigma. And then I have this sum. Yes? Okay. But this sum is also very famous. You have studied it in high school. What is this sum called? I intentionally said high school. Now your prestige is at stake. Yes. It's a geometric sum. Yes? Because every time the lambda is being multiplied. Okay? But I don't like this kind of limits. Let us change the limits of sigma to more natural one. So let us start with 0. So if I start with 0, so it means I go from 0. So here I have to write n minus. Okay, let me write it like this. So let me keep this one the same. If I write this one, do you believe this is true or false? So I kept this one the same, yes, but I raised this, I increased it to infinity. Because lambda is positive, this one has more positive terms in it than this finite one. So it is guaranteed that this sum is definitely less than this sum. Yes? Okay, now this is a famous geometric sum now. Now I will reduce the index. So I want to start from 0 to make it a standard geometric series and up to infinity. But when I decrease it by n minus 1 unit, I have to add to the counter n plus 1 unit, yes? So this becomes n plus 1, k plus n plus 1 minus 2. Do you agree what I am doing? I reduced n plus 1 from this lower counter, but the price I have to pay is to add n plus 1 to the counter inside the sigma. Yes, instead of k, I wrote k plus n plus 1. This is exactly the same sum. Okay, but now what happens? This becomes n plus 1 minus 2. It becomes n minus 1. Lambda n minus 1, I bring it out. And then I have this sigma. Lambda to power k. Are you following? Okay, but this is very, very simple. Do you remember a formula for it? This is a very, very interesting sum. You need to know lambda k from 0 to infinity. It is lambda to power k. So it is 1 plus lambda 2 plus lambda 3. It's up to infinity. And lambda is between 0 and 1. So this series converges. It is a geometric series. And it converges to what? To 1 over 1 minus lambda. These are very standard formulas. You need to know them by heart. Or at least you need to remember this is a geometric series. Okay? So then this, I put it here. What happens? This becomes lambda to power n minus 1. And then I have, so let me write it like this, dp2 p1. And then finally, instead of this sigma, I can use this. This is the sum of geometric sum. So it is, and this is crucial. If it was not like this, then this is not convergent. There is no sum for it. So that is, you see, it was very crucial that it should be lower than 1. Okay, so then it becomes 1 over 1 minus lambda. Okay, so I hope that you are following me. This term was what I wanted to estimate by these gymnastics. Finally, I found that this one is less than this final number that you see. So let me register it here. So d pm is less than or equal to lambda to power n minus 1, 1 minus lambda dp2 p1, and that is your estimate. And of course, there is one assumption here. What was my assumption from the very beginning? If m is greater than n. Yes? So, now can you finish the proof? Do you remember what I was doing? Let us review. I randomly chose one element from X, and I started using my contraction map to make a sequence for you out of nothing, more or less, recursively like this. My big claim is that this sequence will converge to a point. That point is your fixed point that you are claiming, and then I will later teach you that prove you that this is the only one. But I told you that instead of tackling the big claim, let us break it into parts. First, I estimated the distance between consecutive terms using my definition and my contraction. And then my goal is a small claim number 1 is that one. Another claim, which I call it claim 2, which was not that small, I want to prove that my sequence is Cauchy. Why this is useful? Because I am working in a complete space, and if I can prove this is Cauchy, I reach the goal that is convergent. Okay? But for proving that this is Cauchy, having the estimate between consecutive terms is useful, but not in exactly what I want, because in Cauchy, I want the distance between any two terms. So I use that estimate to somehow be able to estimate the distance between any 2 points. And I finally got this formula by this more or less simple calculations. Is that right? But now I want to wait for you because it is a matter of one statement. Why do you see now it is Cauchy? Why the sequence is Cauchy by this new estimate? And be careful about that. Lambda is again crucial. It's between 0 and 1. So don't get confused. On the right-hand side, do you have a variable or a constant? P1 and P2 are just fixed 2 points, so that number is constant. Lambda is the contraction number given you from the beginning, so that's constant. So the only thing that here changes is n. Okay? So I have written this estimate. So now, do you agree, what is the limit of lambda to the power of n minus 1 when n goes to infinity? Lambda is somewhere between 0 and 1. Between 0 can be included, 1 not. So do you remember what is this? This is a very famous limit, yes?
It goes to 1.
No,
sorry, 0.
It goes to 0. So this limit is 0. So what does it mean? This is a fixed number, this is a fixed number, and lambda to power n minus 1 can be made arbitrarily small by making n very big. So if I choose n big enough, then this number, because of this, can be made smaller than any number that I like, including the epsilon for the Cauchy part. Is that right? That's the reason. So this distance, so for example, this is greater than or equal to 0, you can calculate this limit, n goes to infinity, it is 0, the left-hand side is 0, the right-hand side is 0, so it means it is sandwiched, it is 0, because of a squeezing theorem. So this means that if you keep m fixed, but n cannot go. Is this estimate n or m? Yes, that is n. Yeah, that's the calculation. Yes, that's correct. Yes, because, yeah, that's correct. Because when n goes to infinity, n is also greater than m. Yes, that's correct. Yes. So this means that because the right-hand side can be made arbitrarily small, so this means that this sequence is Cauchy. So, but what I want you to do is, as an exercise, make this statement, make this argument rigorous. Okay? But this is, I mean, just one line. It's not very hard. Because we know that this can be made arbitrarily small by choosing n extremely large and because m is greater than that. So that's correct. So it means that from some point onward, this can be made smaller than any pre-assigned number epsilon. So now this is Cauchy. So what we can conclude, we can finish it before the break. So what we can conclude now, so Pn, so now we have Pn is Cauchy in X, and X is complete. Therefore what happens? Pn converges. Let P be the limit of Pn. We prove that phi of P is equal to P. Is the idea clear? So we've proved that this is Cauchy. We are working in complete space, so it is convergent. When it converges, it means that it converges to a point. So let P, of course, P should be in X as well. Let P in X be the limit of Pn. We prove that phi of P is equal to P. Okay, so to do this, I would say let n be any natural number. Okay, and then I want to make them equal. I want to prove that they are equal. So let us look at the distance between them. So the distance between phi, P, and P. Let us look at the distance. Because if I can prove the distance is 0, I have shown that they are equal. So my goal is to prove that this distance is 0. Okay? So I have fixed one n. If you want, let me call it n naught. So let n naught be in n. So do you agree with what I am writing now? So this is n naught. So I have chosen one n naught there, and then what I have done, I have used the triangle inequality by bringing that dot inside it, yes? So my goal is to show that this is 0. Okay, so how can we prove that this is 0? Okay, so what I want to do, it might be that is, I hope that you are not confused. Let me put it n, because I want to send n to infinity. It is usually when you fix n naught, you think it's a fixed one. I am writing this for any choice of n. So do you agree for any choice I can write this? And on the left-hand side, I have a fixed number, which I don't know what that is. But on the right-hand side, I do not have a fixed number. I have something that depends on n. So the right-hand side is a sequence because it depends on n. And what I know a number is less than any term in a sequence. So when I take the limit from the left-hand side, this is a constant, so the limit becomes itself. The limit on the right-hand side becomes something, but that something, that limit should be greater than this one. So what I will do now, I will send n to infinity. Let us see what happens. Or should I do something before sending it to infinity? Let me think a little bit. Yes, I have to do something first. I have to write this one is less than, I want to use my contraction. This is smaller than this one. Yes, because that's a contraction. So this part is less than or equal to this one. And that one can be written as Pn plus 1 and P. Yeah, that's better now. So I chose 1n. For that 1n, I wrote the triangle inequality. This is very simple. But why I could make this smaller than that one? Because that phi is a contraction. So the distance between these two should be less than or equal to lambda times the distance between the points. And why I could write this one here? Because it was my definition, do you remember? Phi of Pn is Pn plus 1. So I wrote it here. Do you agree? Now everything is ready. So let me copy and paste this side as well. Now I want to send n to infinity. Okay? So what happens to the left-hand side? Nothing. Do you agree? So why? Yes, that's correct. So this becomes nothing because it doesn't depend on n, so it remains constant. So this becomes what? Can you tell me? Then I send n to infinity. This becomes lambda copy-paste, d copy-paste, p copy-paste. But what can I write for Pn when n goes to infinity? Converges to p. So this means this becomes dpp. But one more thing. What happens to this one? P is copy and paste, copy and paste. What happens to p sub n plus 1 when n goes to infinity?
It also goes to P.
It goes to p, but can you, I mean, if you write it like that, that's okay, but can you justify why it goes to p? We know that Pn goes to p. Why p sub n plus 1 goes to p as well? This we know. I want you to see Pn plus 1. What is the difference between Pn plus 1 and Pn? It doesn't start from the first term. It starts from the second term. Yes, because if I put 1 here, it gives me P2. If I put 2 here, it gives me P3. So this is not exactly the same thing. It is exactly the same thing except the first term. So what this is called with respect to this one? Yes?
I mean, it goes to P and then it takes.
No, it has a name we learned yesterday. If this sequence, so if this sequence is P1, P2, P3, etc., this sequence does not start from P1, it starts from P2, P2, P3, P4, etc. This sequence is what for this sequence? Is a subsequence. And yesterday we learned that if the sequence goes to P, every subsequence will go to P. So this is a better way to understand that. So this subsequence also goes to P. Okay? But what is the distance between P and P? 0. This one is also 0. So it becomes 0. So this distance is less than or equal to 0. But the distance cannot be 0. What does it mean? It means phi of P is equal to P. Okay? So is the theorem finished or what? Something is left? Yeah, just tolerate a little bit, it will be finished. Okay? So is it something left? Yes, this exclamation mark. So I have to prove that that is unique. So how can we prove that it is unique? So let me write it here. So if I want to prove that this is unique, what does it mean? It means that if phi of P is P and phi of Q is Q, if I have more than one, then I want to prove that P is Q. Yes, by the experience you got now, how should I prove that P and Q are the same? Look at the distance. yes, the distance between P and Q is equal to. Instead of P, I write phi P. Instead of Q, I write phi Q. Yes, but because the phi is contraction, this is less than or equal to lambda d pi and Q. Do you agree? Now, d P and Q is less than or equal to lambda times itself. I bring it to the left and factor this out. So it becomes 1 minus lambda dpq is 0. Oh, sorry, less than or equal to 0. Now, can you finish it up? What type of number lambda is? Lambda is where? Lambda is between 0 and 1. So this one is positive. Yes? D is also positive or 0. If the product is negative or 0, it means that this should be 0. There is no other choice. So this means that dp and q is 0. This means that p is equal to q. Okay? Yeah, so before going for the break, a little bit scan everything in your head because I have to clean it. There is no other board for us. But this method somehow is good to remember. Yes. Okay, so we can have a little bit longer break. Yeah, 4 minutes is good. Yes. Thank you.